Hello everyone, hope you are doing very well. Today we are going to see the theory part 5 of our chapter Alcohols, Phenols and Ethers. So let's begin today's topic, NCERT chapter 7 Alcohols, Phenols and Ethers, theory part 5, and specifically we are going to cover today NCERT section 7.4.2. This is disclaimer. Today's learning objective. After attending this lecture, you will be able to understand the preparation methods of phenols. The topics to be covered today according to the NCERT. First of all, the section 7.4.2, that is preparation of phenols. Then we will solve in-text question 7.4 and 7.5. Then we will also solve an exercise question 7.9 and 7.10. And then we will lastly conclude with the summary. So let's start with the first topic, that is section 7.4.2, preparation of phenols. So let's see the methods of preparation for phenols. In the previous lectures, we have covered the methods for the preparation of alcohols. Today, we are going to see the methods of the preparation for phenols. First method is from haloarenes. Haloarenes can also, from the haloarenes, we can also prepare the phenols, and this process is known as Dove's process. Haloarenes means the arene, that means benzene ring, attaching with a halogen. Second method is from benzenesulphonic acid. So from benzenesulphonic acid also we can prepare phenols. Third method is from diazonium salt. And fourth method is from cumene. That is the cumene and isopropyl benzene. And today we are going to see all these four methods of preparation of phenols one by one. Let's talk about the first method, which is from haloarenes. And this is also known as Dove's process. In this, we take a chlorobenzene, a haloarene, chlorobenzene. Then we heat it with sodium hydroxide at 623 Kelvin and 300 atmospheric pressure. So these are the conditions at which this process carries on. Between the chlorobenzene and the sodium hydroxide, we need a particular temperature, which is 623 Kelvin and 300 atmospheric pressure. After the acidification with the hydrogen chloride, like chlorine undergo the process with the sodium hydroxide in the particular range of atmosphere pressure and the temperature, and after that the product you will got, then you have to do the acidification of that product with HCl, hydrochloric acid, then your final product phenol is obtained. Electron withdrawing group such as nitro group NO2 at ortho or para positions increase the rate of the reaction. So if your benzene ring, if your haloarene have any electron withdrawing group attached to it at the ortho or the para position, this is going to help faster the reaction rate. So if any electron withdrawing group present at the ortho and para position, the rate of reaction will increase. Why? Because the electron withdrawing group attracts the electron density from the benzene ring towards itself, stabilizing the intermediate, and also they make the carbon more electrophilic. Because the electron withdrawing group at ortho and para positions withdraws the electron towards itself, make the carbon more electrophilic at which the halogen is attached. And if it becomes more electrophilic, it will be easier for a nucleophile to attack on that carbon. If we see the reaction, we have initially chlorobenzene, a haloarenes. We reacted with sodium hydroxide at a particular temperature 623 Kelvin and the pressure 300 atmosphere. You will get an intermediate, which is sodium phenoxide. So we have benzene attaching with O negative and Na positive after the removal of chlorine, the halogen from the benzene ring. And then when you do the acidification process of this intermediate with the HCl, hydrochloric acid, so this Na positive will be removed and make a side product with Cl negative, and the H positive will be attached with the O negative phenoxide, and you will get a phenol as a final product. Okay, now in this benzene, in the initial benzene, haloarene, chlorobenzene, if any electron withdrawing group is present at particular ortho and the para positions, then it will going to withdraw the electron, make the carbon more electrophilic, the carbon at which the chlorine is attached. When chlorine will removed, the electron withdrawing group increase the electrophilicity of the carbon and make it very easy for the nucleophile to attack on that carbon and gives us a required product. Okay, that's why we said that electron withdrawing group, if present at ortho and para position, it will going to increase the rate of the reaction. That is Dawes process. Let's look upon the second method of preparation of phenols, which is from benzene sulfonic acid. Benzene reacts with oleum. Oleum is sulfuric acid plus SO3. Okay, so when benzene, you take a simple benzene and you react it with the oleum. Oleum is H2SO4 plus SO3. What will happen? The reaction will happen and you will get a benzene sulfonic acid. Okay, then the benzene sulfonic acid is then heated with the molten sodium hydroxide and you will get a sodium phenoxide. Okay, then that mixture is again acidified to obtain our final product, that is phenol. If you look upon the reaction, we have benzene ring, which is our initial reactant. You react it with oleum, H2SO4 plus SO3. And via this reaction between benzene and oleum, you will get a benzene sulfonic acid. That means benzene over which SO3H group is attached. Okay, now this benzene sulfonic acid is then heated with the molten sodium hydroxide, and the benzene sulfonic acid will convert to sodium phenoxide, and then when you acidify the sodium phenoxide, it will convert to phenol. Okay, and you will get your measure product, which for which the reaction is happening, that is for the preparation of phenol. So you will get your phenol in the end. So this is the second method from benzene sulfonic acid for the preparation of phenol. Now, if we look at the third method, that is from the diazonium salts. We have covered the diazonium salts, right? So aniline is treated with sodium nitrite, NaNO2, in presence of hydrochloric acid at a particular 0 to 5 degrees Celsius temperature range to get us or to form benzene diazonium chloride. You can also call it as BDC. Okay, so aniline, we take the aniline and then we react it with NaNO2 in presence of HCl at a particular temperature range 0 to 5 degrees Celsius, and it will give us benzene diazonium chloride. Then the diazonium salt you get is warmed with the water molecule to produce our major product, phenol. So you have this reaction, you have taken the aniline, a primary aniline. Okay, this is primary because nitrogen is attaching with 2 hydrogens and 1 carbon. Okay, so this is aniline. You react it with NaNO2 and HCl to convert it into a diazonium salt, that is benzene diazonium chloride. Benzene attaching with N2 positive and Cl negative. Then you react this benzene diazonium salt with the water molecule. You warm it and you will get a final product, phenol. Plus N2 gas will be released and the side product, that is HCl, you will obtain. Okay, so this is how the reaction happens and you will get your major product, that is phenol, from the diazonium salt. If we see the next method, the fourth one for the preparation of phenols, that is from cumene. Okay, and this is very most this is very common method for the preparation of phenols. So cumene is actually isopropyl benzene. Cumene oxidized in the presence of air, that is oxygen molecule, to form cumene hydroperoxide. Then that cumene hydroperoxide, when these oxygen molecule from the air is attached with this isopropyl group in the benzene, and you will get a cumene hydroperoxide, then it will react further to form the acetone and phenol on the treatment with dilute acid. So you do the acidification of cumene hydroperoxide and you will get your product as phenol, which is your for the, so this reaction is for preparation of phenol. So you will get phenol, and along with that you will get a ketone, which is acetone. If you look upon the reaction, we have this molecule cumene, which is benzene, over which an isopropyl group is attached. Then when you oxidize this cumene in the presence of air, that is oxygen molecule, these oxygen molecules will enter to the isopropyl group and you will get a cumene hydroperoxide. Okay. Then you do the acidification of this cumene hydroperoxide in the presence of dilute acid. You will get phenol as your major product, and along with that acetone. The acetone byproduct CH3COCH3 you are getting is also obtained in large quantity. So it is double advantage, right? You are also getting the phenol for which you are doing the reaction for the preparation of phenol, and also along with that you are getting a byproduct which is in also a large quantity, that is acetone. So that's why this process of preparation of phenols from the cumene is most common method for the phenol preparation. Let's solve an in-text question 7.4. The question is, show how are the following alcohols prepared by the reaction of a suitable Grignard reagent on methanol. Methanol is a aldehyde, or you can also call it as formaldehyde. Okay. You have to show that the following given two structures of alcohols are prepared by the reaction of methanol and the suitable Grignard reagent. Okay. And how the reaction happens. Okay. That you have to tell. So show how the following alcohols prepared by the reaction of suitable Grignard reagent on formaldehyde or methanol. So the two products given are, two alcohols given are, first is CH3, CHCH3, CH2OH. This is a primary alcohol. The secondary one, second alcohol is actually cyclic hexane, and over which you have CH2OH. Right? So you have to tell that how will you prepare these alcohols by a suitable Grignard reagent reaction with methanol. So let's talk about the reaction of the Grignard reagent with the methanol. Primary alcohols can be prepared from formaldehyde by reacting it with a suitable Grignard reagent followed by acid hydrolysis. So what will happen when you react formaldehyde or methanol with a suitable Grignard reagent? You will get a primary alcohol as your major product. After, of course, the acid hydrolysis of the product, you will get after formaldehyde and Grignard reagent reaction. Okay. So we have also talked about this, that formaldehyde is the only aldehyde which gives us primary alcohols after the reaction with Grignard reagent followed by acid hydrolysis. So the reaction of Grignard reagent with methanol, how it will happen? It include two steps. The step one is Grignard reagent alkyl magnesium halide RMGX reacts with the methanol or formaldehyde, which is HCHO, or you can write it as H2C double bond O. In the presence of ether, this reaction happens and you will get a adduct, an adduct RCH2 OMGX. This is an adduct. When we have understood this also, that the C double bond O has this electronegativity difference. Oxygen is more electronegative, so the double bond electrons, it will shift towards the oxygen, and because R and MgX bond is actually a kind of polar, due to which there is charge a deviation of charge, you can say delta negative and delta positive is present over R and mgx respectively. And what will happen, this alkyl group from the Grignard reagent will attach with the methanol, that is aldehyde, and you will get an adduct RCH2OMgx. Okay, this carbon, because it becomes positive, because the electron of the carbon oxygen bond will shift to the towards the oxygen due to its higher electron negativity. The R is having, from the Grignard reagent, is having partial negative charge, so this R will attach with the carbon of the methanol and gives us an adduct. Then the step 2 involves the adduct acid hydrolysis. So we take the adduct we just got in step 1, react it with the water molecule in presence of reacted with the water molecule, and it undergoes the hydrolysis process, acidic hydrolysis process, and you will get your primary alcohol as your major product, plus MgOHX will be your side product. So this is how the formaldehyde will react with the Grignard reagent to give you a primary alcohol as the major product. By varying the R group of Grignard reagent, or you can say the primary alcohol, different types of primary alcohol can be synthesized. Okay, so in the Grignard reagent, the R group is present. You can vary this R, like you can add it as, you can take it as ethyl, as propyl, as butyl, as isopropyl, in any way. And by varying the R group, you can get different types of primary alcohol by this reaction. Now, let's talk about the first part, the first alcohol given. In the first alcohol, the R group in the alcohol is a isopropyl group. Okay, R group is actually every carbon, or you can say the carbon chain except the CH2OH bond. Okay, because we just have seen we are getting a primary alcohol which is RCH2OH. It is primary because OH is attaching with the carbon, which is attaching with only one carbon, right? So CH2OH is constant. It should be there for making it a primary alcohol, but R can be changed. So in the first part of this question, the alcohol given has R group as isopropyl. So you can see that when the methanol, or you can say formaldehyde, react with the suitable Grignard reagent, which is in this case in the first part is isopropyl magnesium bromide. The Grignard reagent is isopropyl magnesium bromide because the R group, the alkyl group in the Grignard reagent is isopropyl group, because that's how you are going to get a primary alcohol in which the isopropyl group is present as R. Okay, so because the question asks that suitable Grignard reagent reacts with the methanol and then you will obtain the following products. Show how. So we are showing that when the methanol reacting with that suitable Grignard reagent, which is isopropyl magnesium bromide here in the case of first part, when they react in the presence of ether, you will get an adduct which is CH3, CH3, CH2OMgBr. Then the second step of the reaction involves the adduct hydrolysis. Adduct reacts with water molecule and undergo the acid hydrolysis process, and you will get your primary alcohol as 2-methyl propanol plus magnesium hydroxide bromide will be your side product. Okay, so this is how you will get the first alcohol given as the product after the reaction of methanol and a suitable Grignard reagent, which is isopropyl magnesium bromide in this case. Now, let's see for our second part. So in the second part of the question, we have a cyclic alcohol. So the R here is a cyclohexyl group because the cyclic, you can say cyclohexane is attaching with CH2OH in the second part. CH2OH has to be there in the primary alcohol, so the other R group is remaining is cyclohexyl group. So the reaction happening is the two-step. The first step involves the methanol or formaldehyde reaction with cyclohexyl magnesium bromide, a suitable Grignard reagent, to give us an adduct after the reaction with ether, that is cyclohexane attaching with CH2OMgBr. This is an adduct. Now it undergoes the acid hydrolysis process in presence of water molecule. This is the second step, and you will get a cyclohexyl methanol, which is already given in our second part of the question, and you will get your final product as primary alcohol. Okay, so this is how in the second part you will get a primary alcohol, which is given, which is cyclohexyl methanol after the reaction of methanol and cyclohexyl magnesium bromide. That is the Grignard reagent, where R is cyclohexyl group. Let's solve the another in-text question, 7.5. Question is, write the structures of the products of the following reactions. So we have given 3 reactions in this question. The first one is a propene or prop-1-ene reacting with water molecule in presence of H positive or acid catalyst. You have to write the structure of the product you will get. Second reaction, we have a cyclic, you can say hexane ring attaching with double bond O, and at the other position we have CH2COOCH3, and you are reacting it with a reducing agent, that is sodium borohydride. You have to write the structure of the product you will obtain. The third and last reaction is an aldehyde, which is CH3, CH2, CH, CH3, CHO, reacting with again sodium borohydride. The product you will get, you have to write the structure of that. Okay, so let's see for the first reaction. So for the first reaction, the acid, that is H positive presence, protonates the double bond present in the propene and forming a stable carbocation at the secondary carbon, because secondary carbocation is more stable than the primary one, and the tertiary carbocation will be more stable than the secondary one. But here tertiary carbocation is not possible. Secondary carbocation formation is possible. So H positive protonates the double bond and form a secondary carbocation, which is the stable carbocation. What will happen? Water will attack, then water molecule will attack the carbocation, and you will form a protonated, you can say, compound. Okay, then what will happen? Deprotonation happen of that protonated compound, and it will give you a alcohol as a product. So what I'm saying, the reaction is, we have propene, CH3, CH double bond CH2, right? You react it with H positive, acid catalysis, it undergoes acid catalysis process, where the H positive is going to protonates the double bond present in the propene, and you will get a secondary carbocation. So H positive will attach to the CH2 carbon of the double bond, and you will get a CH3, CH positive, CH3, a secondary carbocation, which is stable. Now the water molecule will react with this carbocation, attack on this carbocation, and form CH3, CH and O positive HH. Okay. Now what will happen? You will get, after the deprotonation process, you will get a alcohol product. So one H positive will be removed, and the oxygen will attracts the hydrogen oxygen bond electrons towards itself and form a stable alcohol, that is propane 2-ol. I hope you understand that first of all, we like H positive, that acid catalysis happen over the propene. The double bond will get protonates and form a formation of secondary carbocation happens. Then the water molecule stabilize this positive charge of the carbon, that is carbocation, and form a protonated compound. Then from that protonated compound, we have O positive in that, right? So what will happen? One of the H positive from from O positive will be removed, and the sharing electrons of hydrogen oxygen bond will be attached or will be moved towards the oxygen to stabilize its positive charge, and you will get a stable propane 2-ol, that is CH3, CHOH, CH3. Okay, so this is the structure, or this is the product you are getting in the first reaction. Now, for the second reaction, we have given the hydride from sodium borohydride attacks the carbonyl carbon, C double bond O carbon of cyclohexanone and forms an alkoxide ion. Okay, so from the sodium borohydride, hydride will attack on the carbonyl carbon of the cyclohexanone. We have ketone, cyclohexanone, and will give us an alkoxide ion. Actually, we use the sodium borohydride for this hydration process of carbonyl compound. Then what will happen when you get an alkoxide ion? The protonation of that alkoxide ion happens, which gives you an alcohol. Ester group remains unchanged. The ester group is also present in our second reaction reactant, right? But that will remain unchanged. Why? Because the sodium borohydride is a mild oxidizing agent. It is not you can say it is not strong reducing agent. Okay, it is a mild oxidizing agent, due to which it cannot reduce the esters and also acids. So acids and ester reduction need a strong reducing agent, but sodium borohydride is exception, because sodium borohydride cannot reduce ester and the acids because it is a mild oxidizing agent. Okay, so if you have this reaction where we have the reactant as methyl 2-oxocyclohexyl ethanoate. Okay, so you have this carbonyl carbon, C double bond O in the cyclohexane chain, right? And the other part is CH2 C double bond O OCH3, which is the ester one. Okay, so the ester one, the ester group remains unchanged. It will not get affected by sodium borohydride. If there is any presence of strong reducing agent like lithium aluminium hydride, then the ester group will also change. Okay, but here only sodium borohydride is given, so ester group will remain unchanged, and the other C double bond O, the carbonyl group present in our cyclohexane, is going to affected by the presence of sodium borohydride and get reduced. The proton so basically hydride from sodium borohydride attacks on this carbonyl carbon, breaks the double bond O with the oxygen, and oxygen get a negative charge. And then what will happen? The protonation of alkoxide ion, you will get a alkoxide ion, and then protonation of that alkoxide ion happens, which will gives us our final product as a alcohol, which is methyl 2-hydroxycyclohexyl ethanoate. So C double bond O will convert to COH. Okay, so this is the major product you are getting in our second reaction. Let's see now for the third reaction given. So again we have sodium borohydride in the third reaction as a catalyst, as a reagent. So hydride again from the sodium borohydride attacks over the carbonyl carbon of the aldehyde and forms an alkoxide ion, because in the third reaction reactant we have aldehyde, right? CH3, CH2, CH3, CHO. CHO is aldehyde. So C double bond O and H. So that carbonyl carbon, C double bond O, the carbon is going to attacked by the hydride from sodium borohydride and gives us an alkoxide ion. Then that alkoxide ion undergoes the protonation process and you will get a primary alcohol as the product. If you talk about the reaction, you can see that we have this reactant 2-methylbutanol, that is aldehyde, Al at the end of the name representing aldehyde. And also there is CHO present, that means it is an aldehyde. It reacts with sodium borohydride. The hydride from sodium, the hydrogen from the sodium borohydride attacks over the carbonyl carbon of CHO, aldehyde, and forms a alkoxide. Then the protonation of alkoxide ion happens and you will get your major product as a primary alcohol, which is 2-methylbutane 1-ol. So CHO will convert to CH2OH, a primary alcohol. So this is the major product you are getting after the reaction of the sodium borohydride and the given aldehyde in the third reaction. Let's see an exercise question 7.9. Question is, give the equations of reactions for the preparation of phenol from cumene. So how can you prepare the phenol from cumene? You have to give the reactions equation. We just have seen, right? So you can solve it. So let's start solving. We know that phenol, one of the method of preparation of phenol, or most common method of preparation of phenol, is from cumene by the aerial oxidation or oxidation in presence of air, followed by the hydrolysis. Cumene, which is isopropyl benzene, is first of all oxidized in the presence of air, and you will get a cumene hydroperoxide. Then this cumene hydroperoxide converted to phenol and the acetone. Acetone is also a byproduct but obtained in larger quantity. The cumene hydroperoxide treat with diluted acid, and you will get phenol and acetone, your product. You can see we have this cumene isopropyl benzene attaching with isopropyl. So we do the oxidation of cumene in presence of air. So this oxygen molecule is adding or get substituted into this propyl group and become or gives us cumene hydroperoxide. Then the hydrolysis of this hydroperoxide, cumene hydroperoxide, happens, and you will get your products as phenol and the acetone CH3COCH3. Okay, so this is how the phenol is prepared from the cumene by the given reaction. The next question, the exercise question 7.10. Question is, write the chemical reaction for the preparation of phenol from chlorobenzene. Now you have to write the reaction for the phenol preparation from chlorobenzene, haloarene. Phenol can be prepared from the chlorobenzene, which is a haloarene, via Dawes process. We have seen the Dawes process. What is it? So in this Dawes process, step 1 includes the treatment of the chlorobenzene with the sodium hydroxide in a particular temperature and pressure. And then chlorobenzene, when treated with sodium hydroxide at 623 Kelvin and 300 atmospheric pressure, it will give us sodium phenoxide and sodium chloride. Then step 2 includes the acidification of sodium phenoxide. So the sodium phenoxide you get from the step 1, you do the acidification of that in presence of H positive. So sodium phenoxide treated with hydrochloric acid, and you will get a phenol as your major product. Reaction involves, you take a chlorobenzene, react it with sodium hydroxide, and you will get sodium phenoxide when the reaction is happening. And also this reaction, this is step 1, happens on a particular temperature, 623 Kelvin and 300 atmospheric pressure, and you will get an intermediate sodium phenoxide, O negative, Na positive. Then it will undergo the acidification process, reacting it with hydrochloric acid, and you will get alcohol. The Na positive will make the side product with chlorine, NaCl, and O negative will attach with H positive and gives us alcohol. That is phenol. One thing I want to add up, remember we have also tell you about the fact that if any electron withdrawing group is present at ortho and the para positions of benzene, it is going to increase the rate of the reaction of Dawes process. Okay, and why it was because if electron withdrawing group is present at ortho and para positions, it is going to withdraw the electrons from the benzene ring, make the carbon more electrophilic at which the halogen was attached, and it will make easier for the nucleophile to attack on that carbon, and you will get a intermediate. Okay, and then acidification of intermediate gives us phenol. Okay, let's look at the summary, the points to remember from today's lecture. So first of all, we have talked about the Dawes process for the preparation of phenol. Dawes process requires very high temperature and pressure in the step 1, and also electron withdrawing group if present at ortho-para positions, it will make the reaction faster or easier. Then we have seen the cumene to phenol conversion, or you can say preparation of phenol from the cumene, and it is a most common method or commercial method used for the preparation of phenol. It includes 2 steps. the step 1 is for the cumene oxidation, where you will get a cumene hydroperoxide, and step 2 include the acidification of cumene hydroperoxide or acid treatment of cumene hydroperoxide in presence of dilute acid to give you the products phenol and acetone. Acetone is a byproduct, still it is obtained in large quantity. That's why this is a very commercial method used to prepare the phenol. We have also seen the benzenesulphonic acid method for preparation of phenol, where we use oleum for the sulfonation of benzene to give us a benzene sulfonic acid, and then that benzene sulfonic acid, when react with the molten sodium hydroxide, it will convert to sodium phenoxide, and then you have to do the acidification of sodium phenoxide. Then the major product, the phenol, you will get. We have also seen the diazonium salt method, where we require sodium nitrite in presence of HCl at low temperature, 273 to 278, like 0 to 5 degrees Celsius, for the diazonium salt making. Okay, and when you get the diazonium salt for the diazotization, so you will get a diazonium salt from the benzene reaction with an NO2 and HCl at a particular low temperature range, you will get a diazonium salt, and then you have to do the water reaction, like react it with the water molecule and a little warm it, and you will obtain the major product as phenol. So these are the 4 methods we have studied today regarding the preparation of phenols. Okay, thank you so much. That's all for today's chemistry session. Thank you.